Randy and Bob thought it would be an interesting talk for this context. And let me just say things about collaborators before I go on. So I'm going to actually tell you two different ways of thinking about the Maxwell equations that are new. The first one was developed jointly with Charlie Epstein some years ago, and that actually is acutely aware of topology. So that's going to be the first part of my talk. And then more recently, Zydrunas, Gimbutas, Felipe Vico, and Miguel Ferrando and I developed a formulation that actually is completely unaware of topology. So I thought that was interesting, and it's not known to have existed before, as far as I can tell. So that's why I call it a new potential theory. And then there's some other work that, if I have time, I'll get to, that's joint with Mike O'Neill, Alex Barnett, and Andreas Klockner. OK, so the whole talk is going to be about electromagnetic scattering. And to remind you all of the context, the standard problem is we're looking for solutions to Maxwell equations in the frequency domain. So time harmonic solutions. So E is going to be the thing I care about, bold E and bold X. They're now only functions of space with a governing frequency, which is k. OK, so if you do that, then the Maxwell equations just take the form curl of H is some scalar multiple of E, curl of E is a scalar multiple of H, and they're both divergence free. That's electromagnetic scattering. And the language of scattering is basically that you think of as the total field as the sum of an incoming field and a scattered field, both for E and H. So generally, you know E incoming. You're trying to compute either the total field or the scattered field. And in this talk, I'm going to concentrate almost entirely on perfectly conducting boundaries. So we're going to have a domain that's going to consist of some number of objects in 3 dimensions. I'm going to assume, just for the sake of simplicity, that there are no nasty corners and edges. They're just smooth boundaries. And the boundary conditions that are classical on perfect conductors are that the tangential components of the electric field vanish. So that's n cross E, where E is the total field. But if you think of that in terms of a boundary condition, you can think of it as a tangential, an inhomogeneous boundary condition on the tangential components of the scattered field. So n cross E scattered has to annihilate n cross E incoming. And the same is true for the normal component of H. OK. And of course, this is a scattered field, so it has to be a radiating solution. So there's a standard condition that the radiating solution has to satisfy at infinity, namely the Silver-Muller radiation condition, which is just essentially the full Maxwell analog of the Sommerfeld radiation condition for an acoustic wave. OK. So I'm going to talk a little bit about the Hummels equation just to motivate the numerical issues underlying solving wave scattering problems. For those of you who don't think about this too much, I'll very briefly go through the classical vector and scalar potential representations, talk about the classical integral equations that are used to solve these problems, the difficulties they encounter, and then some of these new formulations that we've developed over the last 5-10 years. OK, so here's the Hummels equation. So suppose you want to solve Laplacian u plus k squared u equals 0. That's the equation in free space. And you have a boundary condition u equals f on the surface of a sphere. Is anybody unhappy yet? OK, so if you just write down the separation of variables version of the differential operator, you get the standard separation of variables representation, and you get the standard solution. So the standard solutions, when you put everything together, are in terms of spherical harmonics, right, which are down there at the bottom. And the standard thing to do is to say, OK, in those variables, in spherical coordinates around a scattering center, the solution that satisfies the condition is an expansion in spherical Hankel functions times spherical harmonics. That's just a very standard representation. And if you want to use classical theory to say, how do I solve the problem? A wave is impinged on a boundary and something scatters off. You say, I'm going to represent the solution in this basis with unknown coefficients, alpha and m, indexing the spherical harmonics. OK? And you expand your function, that is your boundary condition, in terms of spherical harmonics. So that's an orthogonal basis on the sphere. You get your coefficients. And then you match coefficients. And that's the answer. So we're all done. Right? So the scattering coefficient alpha and m is simply the incoming wave divided by little hn of k. Problem solved. And the nice thing is that if you plot little hn of k as a function of k, just for some fixed n equals 20, That's the numerical analyst way of saying it doesn't vanish. I can plot it. I didn't see it go through 0. You can prove that, but in fact, it's true, right? So the denominator vanishes. So that's a good thing about classical scattering theory. The problem with it is cheating. Okay? And why is it cheating? It's because I took a sphere and I wrote down an exact representation of the solution in the exterior of the sphere. You have 0 chance of doing that in any other geometry. The closest thing you can do is to say, I still like my spherical harmonics, but I don't know how to do that. I can't represent the solution. What I can represent is functions on the boundary. So suppose that what I do is to write down the solution as what we would call a single layer potential. Right? That's an integral of the Green's function in 3 dimensions, e to the ikr over r, convolved with the density sigma. And if I express that in terms of spherical harmonics, I get this expression here. It involves both Hankel functions and Bessel functions, spherical Hankel functions and spherical Bessel functions. And if I do that and write down the solution just like I did before, match all modes, just mode by mode, go through the system and match, I get a formula for sigma nm. And it's the data multiplied by some Wronskian divided by the product Jn and Hn. And now we have some problems. And we have problems because Jn likes to vanish. It has zeros. So when you divide by Jn times Hn, it hits the origin often. It's a countable sequence of values where the solution fails to exist in this construction. Right? That's a failure of the integral equation, not of scattering, since we just saw there's an exact solution. So this is a mathematical failure, not a physical failure. You'd like that not to happen. There's a standard fix for that. The standard fix is to say, I won't just use the single layer potential. I'll use a linear combination of the normal derivative of the Green's function and ik times the Green's function. And if you do that, you get this more unpleasant formula. But it has the interesting property that the denominator never vanishes. So I'm hiding all the algebra. You just do the algebra. You get something in the denominator. There's my numerical proof that it never vanishes. And for those of you who like special functions, you know perfectly well why it never vanishes, because this is a complex combination of Jn and Jn prime, and their zeros don't occur simultaneously. Since I've complexified it, I just proved that it can't vanish. So this is guaranteed to never break. And that's called the combined field integral equation in the general case. Because what I said here is no longer restricted to a sphere. The proof of invertibility is restricted to the sphere. But the construction says I have an arbitrary surface. I'm putting some continuous function on that surface that I think of as a mixture of charges and dipoles. Charges, because that's what we think of as the Green's function, and dipoles, because that's what we think of as its normal derivative. OK? All right. And of course, that's still useless because it was still restricted to a sphere. We need to do this to surfaces of arbitrary shape. So how do you do that? And that's also completely classical. The classical way is to represent electromagnetic fields in the Lorentz gauge by stating that E is IKA minus grad phi, that H is the curl of A, that the vector potential A is the convolution of that same Green's function with a current, which we're going to call J, and that the scalar potential is the convolution of G with a scalar function, which is the divergence of J divided by IK, which for those of you who are physicists is called charge. Right? OK, and again, the Green's function is just IKR over R. OK. So if you do that, if you just use this representation for the electric field and impose n cross E scattered equals minus n cross E incoming, you get the electric field integral equation. If you impose that n cross H is equal to current, which is another condition that's true on perfect conductors, you get the magnetic field integral equation. So these are both equations that you can pose on surfaces of arbitrary shape, arbitrary genus. There's nothing about a sphere here anymore. These are very general representations. The problem is they break just like in my, that's why I start with the simple cartoon of the sphere and the single layer potential. Both of these equations fail at a countable sequence of spurious resonances. The integral equation simply fails to be invertible essentially because in a given geometry, it breaks whenever there's an interior resonance of the corresponding equation, and you didn't inform the integral equation that you cared about the exterior or the interior, and that's why it fails. So you have to break that somehow. And that's been broken too, and it was broken exactly the way I broke it on a sphere. What you do is you take some strange linear combination of the magnetic field integral equation and the electric field integral equation, and it's resonance free. So this problem has been solved in the general case. All people who do computational electromagnetics are aware of the existence of an integral equation that is always invertible. It unfortunately isn't a Fredholm equation of the second kind, which means it's ill-conditioned, or has the chance of being ill-conditioned, which it wouldn't if it was a resonance-free Fredholm equation. Okay? The second thing that's funny about electromagnetics is that things go very wrong as the frequency goes to 0, which is obscured in almost all textbooks on this subject. And we're going to try to unobscure it. Is that a word? Okay. All right. So what's wrong? So here's the first thing that's wrong with the classical representation of electromagnetic fields. You're writing E as IKA minus 1 over IK times the gradient of the scalar potential, which means that I'm trying to construct an electric field with terms that are of order k and terms that are of order 1 over k. And you think good things will happen as k goes to 0. And it's just, you should not expect good things to happen, and they don't. And they have not fixed the problem, they just give it a name. So in the community, this is called low frequency breakdown. Okay? And low frequency breakdown means everybody's code loses all of its digits as k goes to 0. And you have to fix it. Okay? Now, another thing that you see in all textbooks is that the magnetic field integral equation is supposed to be well conditioned as you go to 0, because it actually is a Fredholm equation of the second kind. It's the electric field that's causing all the trouble. Turns out, however, that the magnetic, even if you solved it this way, you'd still have to compute E from this representation, and you'd still lose all your digits. So even though this is well conditioned, if you want to construct the electric field and not the magnetic field, you have trouble. All right, so how do they fix this? The standard way to fix this is to say, OK, I think I know what happened. I had a vector field, which is current on the surface. I want its divergence. And I also want to know the total vector field. Maybe I can construct a basis in which getting that divergence out is not so hard, and I don't have to divide by IK and match it up with terms that are larger. So there's a whole machinery in the computational electromagnetics literature that talks about constructing bases which essentially are imposing a Helmholtz decomposition on the current on the surface into divergence-free parts and curl-free parts, so you can separate out unknowns and not have this scaling problem. Okay? Let me skip the second part. The other thing that is almost never discussed is that as the frequency goes to 0, in fact, it's not even true that the magnetic field integral equation is well behaved. It's only well behaved on surfaces of genus 0. As soon as there is a hole in the surface anywhere, the magnetic field integral equation develops a null space. And it develops a null space that corresponds, in fact, to intuitive currents that might be flowing around that only give rise to an interior field, not an exterior field, and they're invisible in the exterior. It's a countable null space, so we know what they are. And mathematically, it turns out they are simply the tangential components of the exterior harmonic Neumann fields. So for those of you who don't remember what that is, a harmonic Neumann field is something that's curl-free, divergence-free, and for which the normal derivative is 0. And if you're simply connected, that means you're 0. But in the general case, it permits the existence of a finite number of other fields. That's them. Okay? And it turns out their tangential components are exactly the null vectors of the MFIE. Okay. So how do we fix that? So this is just a plot. So this fact is discovered periodically. This was known to topologists some time ago. This was forgotten in most computational electromagnetics codes until they discovered things were going very wrong when k went to 0. And so many people have essentially, this is one of the best groups in electromagnetics. And what they discovered was everything that was known in pure mathematics but not to the electrical engineers. They essentially reinvented everything that was required. They understood what the exterior harmonic Neumann fields are. They knew how to count the genus. They knew how to fix it. And this is just a plot of what those null vectors are. Okay? So you go to 0, and you can't see those. If you see those, you get into trouble. So it's a very nice paper that essentially is a very easy to read introduction to all of the relevant algebraic topology. Okay. So here's the kinds of things you can do with very elementary mathematics that seem to have been forgotten. So what I want to do is to say, OK, the magnetic field integral equation breaks as you go to 0 frequency. is there an extra condition we can impose on the linear system that gets rid of that null space? So, OK, so what else might we know? So this is nothing but Stokes' theorem. So here's the trick. N cross E is 0. That's our boundary condition, E being the total field. That means any line integral of E is 0. That means the line integral of the scattered field had better kill the line integral of the incoming field. And Stokes' theorem says the line integral of the incoming field is the integral over the covering surface of the curl of E dot n. But Maxwell's equation says that's IKH dot n. OK, are we together? So that's repeated here. What we just said is that the integral of the E scattered has to match IKH in dot n as a surface integral. That means I'm going to divide both sides by k, and then let k go to 0. Now that's safe over here because there isn't a k. It doesn't look safe over here until you notice that E, by construction, is IKA minus grad phi. Well, the integral of grad phi vanished long before I divided by k. So if you do your limits correctly, drop that out, the k's cancel, and you get a condition. Namely, that the line integral of the vector potential on an A cycle simply has to match the flux of H through the corresponding surface, and that's given data. So if you add that condition to the linear system, you keep all your digits. This is a numerical simulation with k starting from 1 going to 10 to the minus 15. If you don't add that condition in, what happens is that all your digits disappear because they're supposed to disappear. You're epsilon away from a non-invertible linear system. So you just get noise back. OK. So a much more extensive line of thinking along those lines, which Charlie and I worked on for a number of years, resulted in the following. So I'm just going to summarize what it says without going through either the proofs or any more motivation. I will say that without giving this introduction, if I just gave you the punchline, we'd go home in about 10 minutes. So that wouldn't be any good. So I'm going to tell you how we got there. OK? So the problem, as in all computational electromagnetics codes, is that the unknown is current. Current being a vector field on the surface. And we believe that it's a meta theorem that if that's the unknown, you're going to get into trouble no matter what you do, because you need its divergence, and you have to divide by k, and that's not right. So what we sort of heroically tried to do was to come up with a construction for a vector field on the surface for which the divergence came out for free, and there was no instability. And the way to do that is, instead of having current be the unknown, think of two scalar functions on the surface as being the unknowns. So physically, those two functions are charge and magnetic charge. Right? Magnetic charge not existing. And when I tell non-mathematicians why I do this, we say there has to be some excuse for having mathematicians in the world. It's sometimes to come up with representations that are non-physical that give you a better mathematical approach to the problem. So we're going to take, instead of current, charge and magnetic charge as the unknowns, and construct current from them non-locally. Non-locally means I have to take that as an unknown. There's the IK here, by the way. I take charge as an unknown and invert the Laplace-Beltrami operator on the surface to spread it everywhere and take its gradient. Step one. Step two, repeat the exercise with the magnetic charge, but whoops, that's supposed to be an n cross. Rotate it and then take it back. Oh no, curl of n, that's OK. That puts it back into space. Right? So we've now constructed a vector field on the surface from this construction. We'll get to this term in a minute. And if I take the divergence of J, what you get is IK Laplacian inverse rho. So it satisfies the continuity condition that the divergence of J is IK rho. And I don't have to construct rho from J. I construct J from rho. So there's no instability anymore because my basic unknowns are charge-like quantities, not currents. The price you pay is that we have to do this very non-local construction to build currents every time we see one. But I like doing that kind of thing. I spend most of my life trying to do these things fast, OK, which we're not going to talk about. But the other term that's here, I think everybody who's a topologist will recognize, and that comes from the fact that if I have an arbitrary vector field on a surface in 3 dimensions, it cannot be expressed as a gradient and a curl. You also need harmonic vector fields. So this extra business here, which is JH, is those components of the vector field on the surface which are divergence-free and curl-free and aren't 0. And by Hodge theory, we know exactly how many they are. There's exactly G of them on a surface of G, or 2G of them on a surface of genus G. And what we need, therefore, is a basis for them. So you can construct well-conditioned Ferrando equations for the unknowns rho, rho m, and a basis for the harmonic vector fields that has resonance-free, no ill conditioning, and is perfect in every way. Because in some sense, this is the right underlying physical construction. As the frequency goes to 0, electromagnetics is supposed to recover electrostatics and magnetostatics. No standard integral equation does that, because the limit as k goes to 0 of full Maxwell is still involving current, and current is invisible when you're doing electrostatics. If you take this formulation and let the frequency go to 0, you get charge as your unknown. And that's the right unknown when you're doing electrostatics problems. And you get magnetic charge as the unknown, which is correct if you're doing magnetostatics through the scalar potential. And there's this annoying extra little bit that you have to worry about that comes from genus. Okay? But you see what I mean? In terms of these unknowns, full electromagnetics gracefully decomposes into an electrostatics problem and a magnetostatics problem. And that's not true from the standard representations. OK, so there's some extra conditions we have to throw in like this when I went through quickly. OK? The downside of that is topology is not your friend. Right? If I took an object with 50,000 holes in it, I now have to construct 100,000 basis vectors for harmonic vector fields on the surface. That's sort of annoying. And there's a pure mathematical question that you could ask yourself, which is there a limit? Is there a way of writing down full electromagnetics so that as the frequency goes to 0, you're completely unaware of topology? Okay? So that's the question I want to ask now. And what we just saw is that you can't be unaware of that because you're seeing magnetostatics as the limit when the frequency goes to 0, because your unknown is current. But let's back away a little bit and say, OK, we're going to let E equal IKA minus grad phi. Right? That's the standard textbook representation. If I could make n cross A scattered equal n cross A incoming, and I could make n cross grad phi scattered equal minus n cross grad phi incoming, I'd be done. Because then n cross E would be 0 by obviousness. Right? Well, the problem is this is a very messy way to try to do business, because A scattered and phi scattered are not even uniquely determined in the Lorentz gauge. Right? If A scat and phi scat are a potential pair that gives rise to the electromagnetic field, so are A prime and phi prime by this construction. Okay? So you're not about to find a good solution to A scat and phi scat. It's not well posed. Okay? So the question is, can we mess around with this in such a way that it's going to be our friend instead of our enemy? So let's go back to electrostatics. So electrostatics says find curl-free, divergence-free fields for whom the tangential components are 0. That's the boundary condition on a perfect conductor. Okay? Well, the amazing thing is if k is not 0, and this were the full Maxwell system, yeah, then there's a unique solution to the PDE that satisfies n cross E equals 0. And as soon as k equals 0, it's not true anymore. There's millions of solutions to this problem. Okay, what are they? Well, they're the problem of capacitance. If I have 17 boundary components, and I set each one to be a different potential, they're a constant potential. Their tangential derivatives are 0. So I've got a 17-dimensional space of stuff that I didn't see that's invisible when k is 10 to the minus 16. That's weird. Something's going wrong there, too. Okay? So, but it says when you take full electromagnetics and go to 0 frequency, in the electrostatics problem, what you see is a null space which is related to harmonic Dirichlet fields. That is guys whose tangential data has vanished. When you take the limit for magnetostatics, what you see is harmonic Neumann fields. They count genus. Okay? So the question is, can we formulate electromagnetics in such a way that what we see when k goes to 0 is the capacitance problem and not the magnetostatic problem? Maybe we have a way of writing down electromagnetics that is completely unaware of topology. All right. So maybe I won't say much more about capacitance except to remind you that if you look for harmonic functions, again, whose tangential components vanished, they certainly correspond to functions which are constant on each boundary component. It's if and only if, right? That's clearly these guys satisfy those guys, but that's all of them. So they count correctly. OK. Right. So here, if you like, these are unknown and arbitrary constants that could be added in. So if I have a scattered field that matches the incoming field up to an arbitrary constant, I did what I wanted to, which is I made n cross grad phi scattered match n cross grad phi incoming. So let's define some quantities on all those boundary components, which are essentially going to be net charge. So they're the integral of d phi d normal, which is the integral of n dot e, which is charge. So let's just look at that number. OK? But the problem we want to solve when the frequency isn't 0 is the full Maxwell equations with this condition satisfied on closed surfaces. This is the divergence of J is I k rho. That's a truism of electromagnetics. Okay? For any k, if I integrate this on the surface, I get the net charge multiplied by I k. What is the integral of a divergence on a closed surface? Well, it's 0. So that means the integral of rho always has to be 0. So when you're doing full electromagnetics, for any non-zero frequency, you're always looking for the solution which corresponds to no charge accumulation on any of the boundary components. You're not allowed to have that. So that's the limit that you're looking for. You can't see capacitance from the non-zero frequency side, because you always want to satisfy this. So if what we're looking for is a representation that's stable all the way down to k equals 0, but k positive. I just don't want it to break if I set k to be 10 to the minus 16. But I'm always going to have to be charge neutral. So these numbers become important. And now we're in PDE world. So in PDE world, the quiz is, if I tell you Laplacian phi equals 0, phi equals f, the Dirichlet problem, does it have a unique solution? You're supposed to say yes. And say, if I tell you the Hummels equation, also with Dirichlet data, does it have a unique solution? You're also supposed to say yes. Okay? If I tell you the vector Helmholtz equation, and n cross a is given, and the divergence of a is h, turns out that has a unique solution for any non-zero k. And if I tell you the same thing when k equals 0, no. Okay, so now we have a problem. That's the problem, that for any non-zero k, things are looking OK, but something is very wrong in the limit. So here's what we're going to do instead. We're going to say, let me not solve the Dirichlet problem. Let's look at the Laplace case. Let me find harmonic functions which are specified up to an arbitrary constant, but where I tell you what the net charge you're allowed to have on that boundary component is. So I have an integral constraint that I'm adding in. This is going to count out as number of boundary components. Okay? If I have 17 components, I have 17 constraints and 17 unknowns. So it's still a square linear system. Okay? The Helmholtz equation, I'm going to treat in exactly the same way. I'm not going to solve the Dirichlet problem. I'm going to say, let's look at the Helmholtz equation where I have Dirichlet data for the scattered field up to arbitrary constants, and I'll impose some integral constraint. Turns out they satisfy uniqueness, and the same is true for the full vector case. That is, this is not the system before. I've added in extra unknowns, little vj, and extra constraints here, where the q's are given. Okay, so this is just a statement. I'm not going to prove this. I'm just telling you as a statement about a PDE. That has a unique solution, that has a unique solution, that has a unique solution, and that has a unique solution. So everybody's happy. And now it turns out that if I write down this boundary value problem for the vector and scalar potentials, this is a PDE system which, if I solve, gives you the full electromagnetic field. So what we've written, this is new. Okay? I have to apologize again for all the horror of electromagnetics. If you're not in it, it's a mess. But I'm in it. Okay? So here's the mess. If you ask essentially any physicist, they will tell you that you cannot write down boundary conditions on the potentials, only on the fields. This is a system of boundary value problems for the potentials, which we can prove is in one-to-one correspondence with electromagnetics for all frequencies all the way down to frequency k equals 0. Okay, so if you do that, here's the theorem. It just says, give me the incoming fields not expressed as incoming electromagnetic fields, but as incoming potentials. That's the trick is, for those of you who are watching, is the boundary value problem I'm going to solve involves not the data in standard electromagnetic form. You have to tell me the incoming potentials, not the incoming fields. But that's always possible. If I have some currents over there that are giving rise to the incoming wave, you're naturally going to write them down in terms of potentials. So there's actually no without loss of generality, you can do that. Okay? And anyway, so this is just a summary that says we can do this. And amazingly, this problem and this problem are uncoupled. So we're going to solve a separate PDE for the vector potential and a separate PDE for the scalar potential. The data is going to couple them because they have to do with the incoming field. But the PDEs are completely separate. So that's why it has this horrible name. We call it the decoupled potential integral equation because we're not good at naming things. Okay? And we can write down integral equations which give you unique solutions. So if you want to solve the scalar problem, we do exactly what I did in the very beginning of the talk, some linear combination of a single and double layer potential for the Hummels equation. Fine. It just does the right thing. I had to add in some extra unknowns that involve characteristic functions of the domains, and I had to add in a bunch of extra constraints, but this is a trivial matter in terms of linear algebra. Okay? So it turns out this is an invertible Fredholm equation of the second kind. And the same thing is true for the vector potential, except it's even more horrendous. This is what we had to, maybe there's a better one. This monstrosity as an integral representation for the vector potential gives you an invertible Fredholm integral equation of the second kind for the full scattering problem. Okay. So I think that's enough horror. Now there's some nice pictures. A little bit like we saw in the previous talk. You'll see.
Why would physicists say you can't do it with the potential? I mean, if you fix the gates, you can't.
Well, because they never wrote it down. So I'm giving you anecdotal evidence. There's no negative result in the book. But when you ask a physicist, say, no, you can't. I've never seen electromagnetics posed as a boundary value problem for potentials. That's what I mean. Well, and you can, so they can't be a theorem to the contrary. Just that people's intuition was that there is no such boundary value problem. Okay, so right. So those of you who are physicists in the room know that in quantum mechanics you will learn that in fact, contrary to popular belief, maybe it's not the electromagnetic field that's important. Maybe it's the vector potential itself. Okay, and so here's just for entertainment. Suppose I take an exterior harmonic Neumann field. Okay, if I look at it satisfies all the conditions that the vector potential wants, which is it's curl free and divergence free and so on. So if I look at that problem and set the scalar potential to be 0, it gives rise to a 0 field on the outside. It's invisible. This is the current flowing around the boundary, which doesn't have an exterior field. Okay, but that's true here too. So you have non-uniqueness. And the question is, did I mean this problem or did I mean that problem? They're both giving you 0 outside. So the AharonovBohm effect is basically the observation that the electron knows what the vector potential is, and when it passed through the center of a torus, it experienced a different vector potential than if it passed on the outside of the torus, even though the electromagnetic field was 0. Okay, you could argue that. You could probably argue, if I were better at quantum mechanics, I could probably argue that there's an alternative explanation that says it does see the fields, but it's seeing the field in the interior of the torus by tunneling. But let's not get into the philosophy of quantum mechanics here, right? In any event, the point is that these very classical functions are actually the things that give rise to this particular effect. They are the currents that have that effect. Okay, so is this useful numerically? Well, this is just a calculation on this spheroid of using the decoupled potential integral equation and a high order discretization just to convince you that we're getting high order accuracy. I am a numerical analyst, so I like such plots. Errors are going down nicely as I increase the number of triangles in the discretization of the surface. here it's plotting, we went, this is down to 10 to the minus 50, just to convince ourselves that we're not losing digits. The convergence rates are staying very flat as you go to 0. You can do this to more complicated objects. And again, things are staying very flat. So these are all behaving well in the regime that we care about. And here is something close to a knot. At least it has the feature that it would be annoying to construct spanning surfaces for the holes here, right? So it's annoying to have to use a formulation that's genus aware. So if you run the decoupled potential equation all the way down to 0 frequency, it's perfectly happy to solve this problem and isn't stressed by the fact that these guys are interlocking. Okay. I won't say more about the numerics unless there are questions. That's just the same calculation at a slightly higher frequency. Let me skip that. That's again for mostly for a numerical analysis audience. This is just to show you that we can get relatively high order convergence on again a fairly simple geometry here. You're just seeing the error in the scattered field as we increase the number of triangles that are used to discretize this ellipsoid. And there is the same thing for a torus. And OK, so this is not at low frequency. That's at 6.4 wavelengths. Right? So otherwise, it doesn't. The solutions look boring if there's no waves. And here, this is a higher frequency calculation of something that's actually not resonant. So there's now a single. The point of showing all these pictures is that the code is completely unaware of what the geometry that's given is. We build electromagnetic scattering codes that take as input the geometry and return the solution. And in the old days, the first thing you had to do in almost every code was to do a little cohomology study. Find out what the genus was, find bases for various spaces, and then go. This just takes the geometry and returns the solution. You can do this for high frequency things. Again, this is just letting the frequency go down to 0 for a bunch of different geometries and saying that it's not sensitive. You can do this for bigger objects. I didn't point out from the beginning. This is sponsored research. So this is work that was supported by the DoD and the Air Force and the DOE. And we can do, a lot of my work has to do with building fast algorithms for these problems. So we can do problems with a large number of triangles on very modest workstations. This is, again, this is an object which is 35 wavelengths in size. These are the
triangles on the surface.
That's the number of triangles discretizing this surface, right? That's right. That's a mock-up of a carrier. There's also 30 wavelengths in size or so. And here's finally a problem with some genus. So this is a European satellite that's out there somewhere. And in fact, this genus is 6 because in between these panels, there's a kind of a gap. These are solar panels out there on the wings. So this is an object with non-trivial genus, and you would have this problem in the low frequency regime of trying to get solutions automatically. And this thing works perfectly well. OK.
What is your infield in these pictures?
So the infield in these pictures is a plane wave. And you can write down what a plane wave is in terms of the vector and scalar potential, as well as in terms of E and H. So these are all the pictures I showed were scattering by plane waves. OK, are there any questions about this?
This is sort of a question that's orthogonal to the direction you've been talking about. Suppose I have an unknown surface and I send in plane waves. Is there some elegant way to tell how many components it has and what the genus is?
We've been thinking hard about this problem, and I don't know is the answer. I think the answer is that unless you're extremely careful, that problem will get very ill posed as the frequency goes down, because in some sense you're really looking for something like if you solve the inverse scattering problem, right? So if I had a bunch of unknown obstacles, and I said, let's impinge on that structure from many different angles of incidence at many possible frequencies, you could ask, can I reconstruct the geometry from scattering measurements? right? That's in electromagnetics or acoustics, that's what they mean by the inverse obstacle scattering problem. The higher the frequency, the better posed that problem is. So eventually they become invisible. So the interesting question is, beyond the frequency, in the frequency regime where it is well posed, what can you say about genus? And so Charlie and I have some, and we don't quite know what the answer to that is. But we suspect it'll be easy to spoof. So I think that, well, I shouldn't speak for him. My current guess is that that's not going to be a very well posed problem. But I could be wrong. Okay, so I could either stop now or change topics for a few minutes and tell you a little bit about quadrature. Does anybody care to hear about quadrature? Okay, why not? All right. So what I buried deep in all of those numerical methods are, how do you do things fast when you have integral operators? I'm not going to talk about that. And how do you do things with high order accuracy, which is an enormous problem for essentially all numerical analysts who think about integral equations. So let's look at them as a model problem. I'm going to go back to 2D because the pictures are much easier to draw. So that's, again, a single layer potential or a double layer potential. The Green's function in 2 dimensions isn't e to the I k r over r. It's the Hankel function h naught. Okay? So it has a logarithmic singularity. Both of these things satisfy the Helmholtz equation. Right? So when you use integral equation methods, your job is to evaluate a single and double layer potential on the boundary, off the boundary, wherever you request it. And the problem is these guys are either weakly singular or strongly singular. So the single layer potential is weakly singular. It has a log singularity. The double layer potential doesn't even make sense necessarily. It's only defined as a principal value integral on the domain, and it has a jump when you go from one side to the other. It's like a Cauchy integral, right? Okay, so the question is, how do we compute layer potentials on a computer quickly? That's the problem of quadrature. And there's many methods out there, so I'm going to summarize decades of work in numerical analysis to say standard approach number 1 is called product integration. That is, I divide my object into patches. On each patch, I work out the exact integral of the Green's function against a polynomial basis function. And I do that patch by patch. And therefore, I get the order of accuracy I expect, because it's underlying that is a piecewise polynomial approximation of the density. So the quadrature problem has gone away, except I didn't really do it. I just said I have to integrate the singular kernel against the piecewise polynomial. I didn't tell you how to do that integral. But since it's a local calculation, you just do it by brute force if you need to. Okay, so there's ways of doing that. There's more fancy ways that say, well, if I'm integrating on a surface, I could change the coordinate system so I'm sitting at the North Pole, right? If I'm sitting at the North Pole and I spread it flat, it's like I'm integrating on a polar grid. And so my integration is r d theta, and the r cancels the singularity. Great. That's called singularity cancellation, which is essentially a change of variables to get rid of the leading order singularity, and so on. There's many such schemes. There's a whole bunch of schemes that have also been invented that have designed remarkable quadrature rules that by pre-computation give you a certain order of accuracy because they're aware of the nature of the singularity. So they're like Gaussian quadrature, which was done for smooth kernels, but they build families of quadratures that incorporate a certain kind of singularity. And they've been extremely effective, and they work in both 2 and 3 dimensions. But we wanted to, so this is, when I say we now, I mean Mike O'Neill, Alex Barnett, Andreas Klockner, and Charlie Epstein again. We're looking for ways of using the following intuitive fact. So if I just take that single layer potential, so here's my discretization points on that black boundary, and I just evaluate the answer by a brute force quadrature, like the trapezoidal rule running around here, totally unaware of a singularity. It's getting 10 digits out here, and it's getting no digits right along the boundary, right? Going anywhere from, it dropped from 10 to 4 out here, and then it dropped to basically 0, which it should. Okay, so does everybody see the colors there? Okay, but you'll notice that it's not that far from the boundary before things get to be good. So the question is, can we exploit that? So Alex Barnett and one of his students started doing this in order to evaluate fields not on the boundary, but away from the boundary. And they had the idea that if I take a point in the interior of the domain, and I construct a kind of a local expansion of the field around that point, maybe I can just evaluate that local expansion right back at the boundary, or up to the boundary, and get good accuracy. And so here's a plot of the error from the naive rule, and the error you get from Taylor expanding the naive rule here and just coming right back to the boundary, and the error goes away. So we said, well, this is promising. Okay, so let's go back to our picture. Here's 50 points on the boundary. Here's where it's good. Sorry, here's 50 points. This is 100 points, maybe. I think that's right. So here's 50 points. Here's the bad region.
Those black things are
the black points are the quadrature nodes. Right? And I think there's 50 of them there and 100 of them here. So h went down by a factor of 2. That is the spacing on the boundary. And you'll notice that the good region shrunk by about a factor of 2. That sounds promising, right? Does everybody believe that by the picture? It's about right. It's even true. So let's turn this into a math exercise. So I'm going to take a point that's off surface. I'll label it C. I'm going to compute the single layer potential not at the target x here or off the surface. What I'm going to do is to construct a Taylor expansion for the net result. So the Taylor expansion for the Hummels equation means an expansion in Bessel functions. So this is just the if it was a Cauchy integral, this simply would become a power series, a Taylor series. But for Helmholtz, that's the right separation of variable solution. So I'm going to make an expansion here, okay? And now I need to know what are the coefficients in that expansion if I just use a smooth rule. Well, the coefficients are if I did the integral all the way around the boundary using the Graph addition theorem. So I took my kernel, which depended on the source and the target. I break it up into pieces. I do the integral. This is just a kind of the pure mathematical explanation of what it is I'm doing here. It really corresponds to just sum up, do the integral like you're an idiot, as if you didn't know it was a singular integral, but do it away from the boundary and get a bunch of its derivatives too. That's what we're saying. And now let's repeat the experiment. So P here is going to be the order of my expansion. So with this is the picture with 80 nodes, P equals 3. And here's the picture with 80 nodes, P equals 6. And you'll notice that right back at the boundary, instead of having no digits, it's getting 3 or 4 digits. When I go to P equals 6, you're getting 6 digits. So okay, if this was a quiz, we'd say, what do you think will happen when I make P equal 12 with 80 nodes? Nothing good happened. Okay? Why did nothing good happen? So so you have to pause and think, how did this go so wrong? And the answer is that's actually right. Because what is the field that you computed the Taylor expansion of? It's the field due to a bunch of point sources. Well, that's called convergence. It's just not the thing you want it to converge to. Okay? It's supposed to be the bad field. What else could it be? Amazingly enough, if I double the number of, so here I went from 80 nodes to 240 nodes, but still with P equals 12, you now see this is now very, very satisfactory. We have 12 digits everywhere. Okay? So that means lurking under this cartoon must be the following facts. A, that when I put a point down inside a domain and compute that Taylor series, under the right conditions, I'm going to get the right answer. And that to get that, I have to carefully control the order of the expansion and the boundary spacing. That's going to be a slightly delicate analytic question. Okay, let me skip that. But before we get that, let me tell you why I like this so much as a numerical analyst. It's that I can take my boundary, dump a bunch of points on it, do smooth quadratures off the boundary, pull it back to the boundary, and I just evaluated singular integrals with no pain. Okay, and what I just showed you is independent of dimension. So we have an enormous amount of excellent machinery for doing two-dimensional problems, a very small amount of machinery that lets us do three-dimensional problems, and this does it in a way that is completely unaware of dimension. Okay, so the scheme is you dump off-surface boundary points, you construct Taylor expansions at all those points, and you pull them back to the boundary. Okay, so there's a theorem, as I said, there is a theorem under there, which is with Charlie and Andreas, which is, okay, what I want, this is the fully numerical scheme. This is my local J expansion, not with the exact coefficients, but with the ones I compute from my discrete quadrature. And I want to know how well does that converge to the single layer potential. So it turns out that error has two components. This is like all proofs in analysis. Right? So one component says the error looks like r to the p plus 1, where r is the distance from the boundary. So the closer I get and the more I crank up p, the more this behaves well. This is a very non-standard estimate, because this is an estimate for the accuracy of a Taylor series without a notion of radius of convergence. Right? For those of you who are analysts in the audience, you recognize that essentially all proofs of convergence always have to do with bounding your radius and the distance to the nearest singularity or something like that. There's no singularity here. This estimate comes from integration by parts. I'm sitting here at a distance r. It's r to the p plus 1 without any underlying notion of where the nearest singularity is. It's just cranking out integrals. Okay? The second part of the error is that I didn't get the exact coefficients, which this pertains to. It says I made an error in the coefficient. And it turns out we can bound that by making sure that the spacing on the boundary is smaller than the radius, sufficiently much smaller that the order of my smooth quadrature will kill this term. So I can control either the spacing or the order of the smooth quadrature. And I can control both. This is a purely numerical error, if you like, a quadrature error. And this is an analytic estimate about a Taylor series. So here's just some pictures now. It tells you that we don't have a standard estimate. That is, this is not converging at a rate h to the p in infinite precision. These error estimates always have the flavor. There's a convergence rate and there's a tolerance. That's how I make my living. So, mixing up tolerances and convergence rates, basically. Okay? So here's a calculation of, here's a complicated geometry in 2D. This is the naive quadrature. So you see it got it perfect everywhere away from the boundary and just messed that stuff up. And so here is just a cartoon of the automatically dropped in extra expansion centers, and then what happens when you evaluate the corrected rule just in that tubular neighborhood of the boundary, you get your 13, 14 digits everywhere.
So when the curvature is higher, you have to be closer.
You have to, yes, that's right. So, and the way that happens automatically, because we do it on the basis of the local spacing of the points, and we assume the user has given us a spacing which itself must have captured the curvature, or it's under-resolved as a geometric question, right? So and that also comes out in the wash. So we don't ask anything about curvature. We just say, what's the nearest boundary point? What's my local spacing? And you step off in the normal direction at 2 times the local spacing. Okay, so here's a high-frequency scattering problem, and done by the same method. And we have fast algorithms for doing all this stuff, which I won't bore you with. Okay, so this is, we're not quite in the geometric optics regime, but it's a very high-frequency regime. And this is simply a blow-up of the solution in this little piece. And this is the 3-dimensional version. So if I have my torus, this is just to show you about where those points are put. That's why we need fast algorithms. We have to evaluate lots of fields in lots of places. We have that. So now we just dump those guys off surface and evaluate it back. And that's a calculation that Alex did, which is, I view this is the flying torus. So scattering, you send a torus up, you hit it with an acoustic wave, and that's what bounces back. The point is we can do quadrature in these kinds of structures now with remarkable ease without even paying attention to the singularities. So that's a big improvement in automating these kinds of codes. So I'll stop there. I'll leave it on the torus. But as I mentioned, this is work that was supported by DOE and by Air Force and the DoD.